last lecture in the series on acoustic materials and metamaterials. So, in this full course we have covered a lot of topics starting from the introduction to the concepts in acoustics, some other advanced concepts in acoustics, and then proceeding with discussion on the traditional acoustic materials such as the porous sound absorbers, the barriers, enclosures, Helmholtz resonators, microperforated panel absorbers, and so on. And then we finally began with the discussion on the new engineered materials called as the metamaterials, which are now used for acoustic purposes. And we have studied two particular metamaterials. One was the membrane type acoustic metamaterials and the second was the sonic crystals. And this last week we have been discussing about the sonic crystals. So, in this last and concluding lecture of this course, I will discuss a few more things about sonic crystals. So, in particular I will discuss about the various factors which are affecting the band gap of sonic crystals. So, how does the various factors they affect the band gap? Then we will discuss some concept called defect bands, and then a brief discussion on what are the applications of sonic crystals, and then I will just give you a few tips and guidelines on material selection, and I will conclude my lectures with a vote of thanks. So, what are the factors affecting the band gap of sonic crystals? So far we have studied how does the sonic crystal operate. It uses two different types of principle. First is the principle of the Bloch's theorem, where a periodic wave is generated inside a periodic structure, and the periodicity, the spatial periodicity or the lambda of the wave is the same as the lattice constant of that periodic structure or the length of periodicity. So, in that case what happens when such periodic waves are generated, all these waves are always quantized and there is a frequency gap between one wave, one mode to another mode. So, always the waves they are quantized and not continuous, and that is why at sometimes it happens that when we are measuring this wave propagation through the irreducible Brillouin zone and trying to see how the wave is propagating, and because all the frequencies are discrete for every mode, then at certain frequency gaps or bands we will get no wave propagation throughout the entire crystal or throughout the entire Brillouin zone. So, those are called as the band gaps. And the other principle was that sometimes a local resonance is created, and during that time usually it is the other principle is similar to the principle of a typical acoustic metamaterial. So, at certain frequencies the effective bulk modulus of the sonic scatterer, it reaches a negative value, and at that suddenly when B becomes negative, then the K vector it becomes imaginary, therefore no spatial wave propagation takes place. So, now what factors they affect the band gap? So, if you vary the size and the geometry of the primitive unit cell of the sonic crystals, then the frequency range over which the effective bulk modulus and density become negative, it can be tuned. So, as you keep changing the size of the unit cell, the geometry of the unit cell and so on, you can keep changing the frequency bands over which you are getting no sound wave propagation. So, this is just like a membrane type acoustic metamaterial, we get yet another tunable acoustic metamaterial. So, the noise control can be tuned by changing these factors within the material. Similarly, the same factor which is the size and the geometry of the primitive unit cell, along with what is the arrangement like, what is the lattice system type, they will determine what will be the Bloch wave that is formed, and hence what will be the band gaps generated. So, we can now list down the individual factors which determine how the shape and the size of the unit cell and the lattice system changes. So, what are these factors? These are the size of sonic scatterers. So, this can also be the variable d, let us say. It is either the thickness of sonic scatterer, or if it is a spherical scatterer. So, let us say if it is a cylinder, so the cross section, if it is a 2D sonic crystal and the cross section is cylindric and it is cylinder in nature, then the cross section will be circular. In the same way, if you have in a 3 dimension, you have a spherical sonic scatterer. So, in that case the diameter, so this is the symbol or I will simply write it like this. So, you can either say what is the thickness, or in other words what is the diameter of the scatterer that we are using. So, that will be the first variable. Then what is the geometry of the scatterer, which means effectively in the direction of periodicity or in the direction of periodicity, what is the cross section like? What is the cross section of the scatterer? Is it circular in nature? Is it rectangular? Is it triangular, and so on? Then it also depends upon the lattice constant. So, we know that thickness of the diameter of the sonic scatterer is one variable. Then we have the lattice constant, which determines the spacing between the scatterer. So, it is the distance between two adjacent centers of the sonic scatterer. So, effectively what is the spacing between the sonic scatterer? And then the filling fraction. Now, if obviously if the diameter and the lattice constant is changing. So, if diameter is, let us say, denoted by a variable d and the lattice constant by the variable a typically, then if a and d change, then obviously the filling fraction will change. Or if the radius and the radius, that is r, and the lattice constant a changes, then obviously the filling fraction is going to change. So, in that case the most important parameter is this filling fraction, and these two are actually this one and this one, they together determine what will be the filling fraction like. So, it changes because the filling fraction changes. Similarly, it also changes depending on the type of arrangement you use, whether you use a square packing, a hexagonal packing, and so on. And then it also depends, so a new factor is there, it also depends on the presence and the distribution of defects within the lattice system. So, what do you mean by defect here? So, here in this course the defect means that, let us say we have this particular lattice system, this is the lattice point and this is the lattice arrangement and so on. So, it is an infinite array like this, let us say, and at each lattice point we have a scatterer placed. But let us say one scatterer has not been placed at one of the lattice point, then this can be called as a point defect. So, here what you have, it means that a scatterer is missing from the lattice arrangement. So, let us say if one of, so it can also, so the band gap will also depend upon this missing scatterer. So, if one of the scatterer is removed from the lattice arrangement, then how will the band gap be effective? We will study about this in the consecutive slides. So, these are the individual factors. So, let us say I am going to here discuss about a paper which was by Wu et al. In 2009. It was a pioneering work which deals with how does the band gap change when a defect is introduced, and how does the band gap change with the increase in the filling fraction. So, two different factors have been studied here. So, the type of unit cell is this. So, obviously this will be repeated and an infinite array can be created, or a very large array can be created, and there is a point defect in 5 cross 5 square lattice. So, a point defect in 5 cross 5 square lattice has been given. So, this particular center or sonic scatterer is missing. Then they have measured is that they kept the R naught, which is they kept the radius of the sonic scatterers. And what were these sonic scatterers? It is a 2D sonic crystal which was composed of polymethyl methacrylate cylinders in a square array embedded in an air background. So, the fluid medium was air, and in the air the arrangements of these polymethyl methacrylate cylinders were made and they had a circular cross section. So, this radius of the cross section of the scatterer is R naught, and A naught being the lattice constant or the distance between the centers of two adjacent scatterers. So, this is a square lattice. So, this is A naught, that this means this will also be A naught. So, R naught was kept fixed, and obviously if R naught is kept fixed, the filling fraction for such lattice system is given by pi R naught by A naught square. So, we have already derived this expression in the very first lecture on sonic crystals. So, when I was discussing with you what is meant by filling fraction, and then what was the expression for the filling fraction of a square lattice and a hexagonal lattice. So, this is the expression for a square lattice, 2D square lattice, which is pi R by A whole square. So, obviously if R is kept constant, then A has to be varied if we want to study the effect of filling fraction. So, they conducted a series of tests where R was kept constant, the material of the scatterer and the background, everything else was kept constant. Only this A naught was varied to get different filling fractions. So, at 40% filling fraction, what do we get is, if you see in this particular band diagram, what is the band gap? So, here this is the band over which there is no wave propagation. So, how do you obtain the band gap? You simply have to find that zone where you have no lines at all. So, the horizontal zone where there is no lines at all. So, it will be this zone, this small zone is the band gap. Then the same configuration was kept, and only the filling fraction was now increased to 50%. So, for that A naught was varied, A naught was reduced. So, now you get a much wider band gap. So, what you see here is that you are getting two individual band gaps, and there is just one line in between the two band gaps. Similarly, when you further increase the filling fraction, you get even wider band gap here and another band gap here and a third one, and just between all these wide band gaps you only have one single line. So, this was a peculiar observation, and once they explored it further, they found was that this single line which is coming in between these wide band gaps is due to the point defect. If there was no point defect, you will have this entire band gap will be together. So, you will get this full band gap here when there was no point defect. Similarly, in case of no point defect, you will get this entire band gap. The line is coming only because of the point defect. That is what they had found over here as well. So, the various observations made and conclusions made from their work was that if you keep all the other factors constant and you vary the filling fraction, then a larger filling fraction leads to a wider band gap. So, usually the band gap occurs around the same region. So, as you can see, it is occurring around the same region, typically around the same region, it is starting from the same region. So, somewhere between 3500 to so somewhere between 3000 Hertz to 5000 Hertz, within that same zone you are getting the band gap. So, the frequency, and the only difference is that from narrow it is getting wider. So, you are getting a much wider band. And then the single lines that are obtained in between, which was due to the defect, was called as the defect bands. So, these are the frequency bands which correspond to the defect in the crystal. So, as we saw here, in a 5x5 crystal, one lattice point was missing or one scatterer was missing, that was creating a defect, and therefore, we get one single frequency line which is a defect band which exists within the absolute band gap. And because of this, which means that the acoustic waves will propagate through these defect bands. So, it is bifurcating the absolute band gap. Now, the frequency of this defect band is also called as the resonant frequency. So, the acoustic waves should be localized. So, what happens is that it has also been found that when the defect occurred, so a simulation study was done, a finite element study was done to find out what is the pressure field distribution in this particular type of sonic crystal array. So, here as you see, the same sonic crystal array is there, 5x5, and a point defect at the center. So, the way it is simulated, what you find is that when the wave front is incident and passes through this structure, then some localized waves are created around the point defect. So, the acoustic waves, they are localized in the cavity or at the point of point defect. So, whenever there is a small gap, a point defect or a cavity, then the waves get localized, which is called as the phenomenon of local resonance. So, which means that compared to the local waves, compared to the other wave fronts inside the crystal, this particular wave will have a much higher pressure. So, suddenly as the wave front is passing through, let us say it is passing through in this direction and going outside in the periodic structure, suddenly at a certain point the pressure will increase. So, it will be sort of a local resonance created at this particular cavity, and that is why the frequency which is corresponding to this defect band is the resonance frequency, because it is that frequency where suddenly a resonance is happening and some waves are getting localized. We get high pressure waves near about at these point defects. However, it does not propagate through outside, so it does not affect the overall noise control, but what it means is that it will bifurcate the overall band gap. So, this is called as the resonance frequency. Okay, so let us see here what is the resonance frequency for this one. So, you see this becomes the resonance frequency. So, if this was the overall, this would have been the overall absolute band. A small line that is coming in between the absolute band corresponds to the resonance frequency, or the frequency at which the pressure waves are localizing in the defects. Similarly, here this was the absolute band, and within this absolute band gap you are getting a single frequency here. So, this becomes the resonant frequency. So, here the resonant frequency was around 4 kilohertz, here it is around 4.5 kilohertz. So, this is just an average value, the resonant frequency is changing slightly over the k vector. Similarly, here you have one resonant frequency here, and then there is another band. So, you get a second resonant frequency somewhere around here, but here the second resonant frequency has not been taken into account, because it was found that the overall effect of this on the pressure wave front was minimal or negligible. So, it was only this particular resonant frequency that is affecting the waveform in the localized acoustic waves. So, these are the 3 resonant frequencies for the 3 different filling fractions. So, how do you find the resonant frequency from a band gap structure? Have a look at the band gap structure and you will observe some anomaly. Let us say you will observe that you have got a wide band gap, and suddenly within that wide band gap you are getting only a single frequency line of wave propagation. So, that single frequency line of wave propagation corresponds to the resonant frequency due to the defect. Okay, so one more study was done to find how do these defect bands of the resonant frequencies, they change with increase in the size of the unit cell. So, the same point defect is there. This is the 5x5 crystal. So, this is the variation of the defect band or resonance frequency. So, a large scale study. So, here the scale size has been increased. Now, when you infuse, this was a 5x5 crystal. Now, here you have a 7x7 sonic crystal array, and you have a point defect at the center. Then the frequency at which you are getting the defect band is almost the same. It is just some point variations, but it has become more stabilized. Now, the variation is not that much. In the same way, as you increase it from 7x7 to 12x7, 12x12 sonic crystal, again the value where the frequency is obtained or the resonant frequency is obtained has not changed much. So, here the average was approximately around 5.17, let us say. Here it was around 5.17, here it is around 5.168 or something, which is close to 5.17. So, the resonant frequency is the same. So, the effect is that as you increase the size of the unit cell, which means that the overall density of this point defect is decreasing in this crystal array. So, in that case the defect bands, they are stabilizing over the entire Brillouin zone. So, you are getting a more and more stable and horizontal frequency line as you plot the band gap structure. So, let us say if you are given a band gap structure and you have a wide band and then you have some frequency line in between that band gap. So, that will correspond to the resonant frequency, but you can see that the frequency line will have some small amount of fluctuations, which means that the size of the array is small and the point defect as compared to the point defect, and for the same point defect, if the size of the array is increased, let us say from 5 cross 5 we come to 12 cross 12 or to 10 cross 10 and so on, then that same frequency line, the fluctuations are going to become less and less, and in the band gap that particular resonant frequency will become more and more horizontal in nature. So, you will get a more horizontal type of frequency line in the band gap diagram, in the band diagram. Similar study was also conducted by Rubio et al. 1999. So, here what they did was they studied about filling fractions and the lattice arrangement. So, here for a filling fraction of 0.41 and for a square lattice, 2D square lattice, and the material was the same, it was 2D sonic crystals composed of aluminum cylinders in air. So, here this is the kind of band gap for this filling fraction and square lattice, and when you increase the filling fraction, obviously the band gaps become wider, the same pattern as observed in the previous paper. But as you also change the lattice form from square to hexagonal, so you are getting another band gap. So, you are getting two different band gaps. Okay. So, now that we have studied about the various effects, then what are the applications of sonic crystals? They are very similar to the application of other acoustic metamaterials. First of all, they are used for sound attenuation. So, two different aspects where they are used. First, for attenuating of sounds or stopping the sound wave propagation, and therefore they are used as noise barriers, especially outside. For example, an outside sculpture or an outside array of trees created between the highway and the residential areas, you can have an array of trees in a sonic crystal type arrangement, and all of that is acting as a noise barrier to prevent the sound wave propagation. Similarly, you can also have sound crystals specifically for the purpose of bending the sound waves, and there you get two important application. One is the acoustic waveguides. So, what do you mean by acoustic waveguide is that it is a structure which is sort of guiding the waves through a particular path. So, the waves, so here the bending will be such that the waves are guided along a particular path, and from point A to B they reach without much attenuation. So, this is more like guiding. And then for imaging purposes, so it is same as the acoustic lens, and we had already discussed the concept of acoustic lens and how does the acoustic lens work. If you have a layer of acoustic metamaterial which has a negative refractive index, so which can bend the sound waves very sharply, then a sharp image can be obtained both from the near field and the far field, and that same concept applies here. So, the details of this acoustic imaging or the use of acoustic super lens is already been, the concept of that has already been discussed when I was discussing about the acoustic metamaterials in general before coming to the membrane type acoustic metamaterials. So, I will just show you the case of acoustic waveguide. So, here you have an acoustic waveguide. So, here these are the individual crystals, and the way this has been done by the author is that he had a typical sonic crystal arrangement, and that was in this form. And here you know that from the analogy of the electrical field into the electromagnetic field into the acoustic field, the refractive index will depend upon the important parameters like the bulk modulus and the density. So, once you change the bulk modulus and the density, you can manipulate the refractive index. So, here the refractive index is continuously changing throughout. So, this is called as a functionally graded sort of sonic crystals where you have. So, let us say suppose you had an array where This one had a, so let's say I am just giving an example, a very rough brief example of graded sonic crystal array. So let us say this is one scatterer with a refractive index of, let us say 5, then you have something with a refractive index of 4, then you have another one with a refractive index of 3, 2, 1 and then 0.5 and so on. And similarly, so this is just in 1D, and the same grading can be done in 2D. So when you go forward, here you will again have 4, 3 and so on, and this from this 4, this will come out to be 3, this will come out to be 2, 1, 0.5, 0.25 and so on. So here the so what it means is that the overall refractive index, it is varying as a linear function along all the directions of periodicity. So if it is a 1D crystal, it will be along one direction. If it is a 2D arrangement, then along both the horizontal and the vertical directions, the two directions of periodicity, the refractive index will be varying linearly, or it will change continuously in the two directions. So that is what is called as a graded kind of solid crystal. So the kind of arrangement that the author was studying is that they have a arrangement of a sonic crystals, and here the refractive index, because it depends on the bulk modulus and the density. So the bulk modulus and the density was varied so as to change the refractive index with the change in the location of the crystals. So it was continuously changing throughout the location. So and a simulation study had been done, and the pressure field has been sort of simulated. So what it is seen is that when a wave front is incident, then most of the wave front goes guided through the sonic crystal and it reaches, so it follows this path. So if I will show you this in different color, so this is the path that the wave front is taking along the crystal, and finally following this crystal. So this is sort of like how you have a hose pipe. You put the hose pipe on a tap and then you have a bucket somewhere at point B, and they are following a very irregular path. So you can have a hose pipe, attach it to the tap, open the tap, and the other end of the tap, and at the other end of the hose pipe you can have a bucket. So here the hose pipe is guiding the it is guiding the water flow from the tap through the different path of the hose pipe and to the bucket. In the same way, this is sort of like a acoustic pipe, which is where if a wave front is incident, it will be guided along the particular sonic crystals and reach from point A to B, and loss will be very less. So it is acting like a typical hose pipe that is used to guide the water. Now we have a sonic crystal guiding the waves. Okay, so these were the various applications. So I'll quickly come to some of the guidelines for material selection. So now we have covered a lot of materials and it's difficult to give a very huge list of guidelines. So I'll just give you I'll just pose a key questions and try to answer them so that you get a hunch of how do you select a particular material. So let's say the first case is where you have to select a low cost, lightweight, eco-friendly solution for a broadband noise control at high frequencies. So when you hear this, you will see the word, okay, so you first of all you want to see what is the frequency range of operation. So here you have a broadband high frequency range, and what are the materials that almost all materials work well at high frequencies, and you use advanced materials only when you need some specific application, because it is usually they are not very readily constructed and they are not very readily available. So when you have a general high frequency application, it is better, and there is no low frequency demand, it is much easier to go for a traditional material. And you need a low cost, lightweight and eco-friendly solution. So once you come with this word eco-friendly, then you would recall that the porous sound absorbers, they can be made with natural materials, like for example you can have a jute fiber composite, or you can have something made with cotton something made with coconut coir and so on, and all of them are able to act as porous fibrous medium, and the sound wave is sort of controlled at high frequencies at a broadband range. So, a porous absorber could be a solution here. Let us say you have another case where you have to do a broadband noise control at mid to high frequencies. So, again it is a broadband noise control mid to high frequencies, and there is no other constraint like a constraint of weight of the material or the cost of the material and so on. So, again for a general purpose solution you can begin with a traditional material, and any traditional barrier material can do the job here, because it is again not a low frequency. So, obviously you can use a sonic crystal, obviously you can use some other advanced micro perforated, you can use a sonic crystal or you can use membrane type things. Actually you cannot, they are specifically for the low frequency. So, for typical mid to high frequencies, so for high frequency purposes it is just a general it is a general tradition to use conventional materials, go for them. Now, we come to the low frequency application. So, let us say now you need again a low cost solution, lightweight, but for broadband low frequencies. So, all of this was for high frequencies and you directly went with the traditional materials like the absorbers or the barriers. Now, for broadband low frequencies, if you think about it, one of the only few material that will specify, that is going to satisfy this condition, is the membrane type acoustic metamaterial, because all the other materials which are designed to work at low frequencies like the Helmholtz resonator or the microperforated panels, even the sonic crystals, they do not have a very broad band gap. It is the membrane type acoustic metamaterial which has a broad band range over which the sound is attenuated, which is from 0 to omega naught, where omega naught is the natural frequency of the unit cell. So, when you hear this thing broadband low frequency, which means you can use an acoustic transmission line or pipe which is made up of membrane type metamaterials as a unit cell. Then let us say you want something for a very selective purpose or very specific noise control at low frequency. So, now the desire is not to cut down all the frequencies at low frequencies. Let us say you have a waveform and only you want to cut down a certain transformer noise or a certain signal. Only a certain signal at a particular frequency you want to cut down, that is the only purpose, you do not want to cut down all the frequencies. So, for that selective operation where only some discrete frequencies need to be cut down, you remember, if you remember very correctly, we had microperforated panels. So, both Helmholtz resonator, panel absorbers and microperforated panels, they all have selective absorption because they only absorb at their own resonance frequency when there is a acoustic coupling. But because out of the three cases microperforated panel gives the maximum absorption magnitude, so that will be our better choice for a selective low frequency absorption or a very discrete and point low frequency absorption. Now, similarly you want something for a outside noise control at a selective low to high frequencies, then sonic crystals could be used. They are mostly used for, because in case of sonic crystals the main limitation is the sizing. So, they are usually used as outside barriers and sonic crystals can be used. So, I have covered the course here and I just give you a few tips on how the various materials can be selected depending on what is the application and what is the constraint like, such as the cost or the weight factor or the type of frequency range you want to cut down. So, accordingly you can go for different acoustic materials. So, with this I would like to conclude my lecture, and when I conclude my lecture I would like to thank a few people who have helped me in this particular lecture series. So, first of all I would like to thank IIT Roorkee and then MOOC and NPTEL. They have given me the opportunity and an appropriate platform where I can create and conduct the very first series on acoustic materials and metamaterials. I am also grateful to my team here. So, my team constitutes in particular it's Sharath from e-learning center at IIT Roorkee and my research assistant Vikram Dutt, who is a MTech student at IIT Roorkee. They have helped me with the recordings of the lectures, compiling of the lectures, as well as with putting up and managing the online portal. So, I would like to thank my team. And I would also like to thank my postdoctoral supervisor, Professor A.R. Mohanty from IIT Kharagpur. It was under his guidance where I learned a lot about acoustics and acoustic materials, and he has been a guiding force in my life. And lastly and most importantly, I would like to thank my family. In particular, I would like to thank my mother Sudha Singh and my husband Manish Kumar Singh. Throughout the creation and the conduction of this lecture, they have given their full support, full understanding and help, which has really made my task very easy. So, thank you to all my team and my supervisors and my family for helping me with these lectures. So, thank you to the audience as well who have enrolled into this course. Thank you.